Welcome everyone. Today I'm going to discuss about the derivations of Schrodinger equation and solving of Schrodinger equations of hydrogen and hydrogen light atoms from quantum chemistry. So we know that the simplest atoms in all the periodic tables is hydrogen atoms because it contains only one electron. However, in this case, we have to consider the hydrogen atoms as two systems. That means one is electron and one is the nucleus. So therefore, if you consider the spherical natures of the hydrogen atoms, the potential energy will be definitely Z E square and divided by 4 pi epsilon naught r. And we know that this 4 pi epsilon naught r is the Boyle's radius. So therefore, and this is the charge of the nucleus and the charge of the electron. So therefore, the Hamiltonians will have two parts. That means one is for electron part and one is for the nucleus. So if you say x1, y1, z1, and x2, y2, z2 is for electrons and the nucleus, then the Hamiltonians will have two part of kinetic energy. That means one is this del one part, another one is this del two part, and this is the potential part. Therefore, we cannot separate this electron coordinates from this nuclear coordinates. Therefore, we cannot separate the variables of this type of equations. Therefore, we have to consider two type of motion. That means one is translational motions of atom as a whole, and another one is the translational motions of the electron and the nucleus related to each others. So therefore, we have a new set from this x1 and x2, x1, x2, y1, y2, and z1, z2 to capital X, capital Y, capital Z, and small x, small z. So therefore, this x, capital X, and capital Y and capital Z is the coordinate of the center of mass of the atoms, and small x, y, z are the relative coordinate of the radial distance. Now, if we talk about the motions, we can definitely separate them as separate entities. Therefore, we don't have any problems of taking these two motions separately in separate variables. So let's say Q is for capital X, capital Y, capital Z, and small r is for small x and small y and small z. That means we can have, so now the psi will be two part. That means it is given here, psi will be two part. That means one is psi, a function of q, and that means capital X, capital Y, capital Z, and psi as a function of r. That means a functions of small x, small y, and small z. So therefore, we can easily separate these two parts. That means one side is the function of q part and one side is the functions of r part. So if we equate this function of q part to a one constant, that means w, then we can easily write this as given here. So therefore, if we rearrange this, we can easily say the Schrodinger equations become, which contain the potential part is this one. As we know, this one is just only a translational motions. That means the equation 3. That means it has already done on the particle in one-dimensional box. So therefore, we don't have any information regarding the hydrogen atoms. Therefore, this is not useful and this cannot be usable. Therefore, this equation is the final Schrodinger equations by considering the motions of the atoms and the relative motions of the electrons and the atoms. And finally, as we know that the size or the weight of the nucleus and the electron is very, very different, more than 2,000 times heavier. Nucleus is heavier than the electron. Therefore, instead of writing mu, we can write simple as m. Therefore, the simplified way of writing, simplified Schrodinger equation will be just as given as like this. So this is the Hamiltonians and this is the eigen constant, that means eigen function. That means E is the eigenvalue. So therefore, simply we can convert this x, y, z, the Cartesian coordinates, into a polar coordinate, as we have discussed in the separate class. That now if it is motion is in rotations, or the hydrogen atoms does not move only translationally, that means it has to be considered the momentum also. Therefore, only x, y, z cannot explain the motions of these hydrogen atoms. Therefore, we need to consider theta and phi. That means the zenith angles and the azimuthal angles, and the r. That means r is the radial path radius. So therefore, we know that this theta angle is the angle made with the z-axis. That means if this is a z-axis, the angle made with this z-axis is called theta. And if you drop down this on the plane of the xy plane, and if you connect this point, then this angle will be phi. So these two angles as well as the r value can change that is called the polar coordinates. So if you change the Cartesian coordinate from the polar coordinate, we know that this del square is equal to d square by, we say, dx square. Therefore, we know now if you change this x, the Cartesian coordinate, to the polar coordinate, we know that x is equal to r sine theta cos phi. Therefore, if you solve the differentiation of d by dx square, d square by dx square for sine theta or cos phi, and if you solve for y and if you solve for x, the Schrodinger equations in terms of the polar coordinate is given as like this. So therefore, this need to be remembers, because we cannot solve the derivations. It's a very long process. So therefore, better we remember this equation as a polar coordinate for the Schrodinger equations. Now we know that this psi is having variables of 3. That means r, theta, and phi. Therefore, instead of writing psi only, we can write r, p, and f. And it is indicated that f is a function of phi, and p is a function of theta, and r is a function of r. So therefore, if you make into this three part, we can do the separations of variables of these equations, these polar equations. Therefore, if you do the separations of variables, first we have to divide these equations by the same sign, as the psi is given here rpf instead of writing psi. Therefore, we know that this r part is a function of r, that means, and p is a function of theta. So we can separate these three, and to simplify it by multiplying this, you can do in your own way. That means how you can separate this theta and r and phi into separate ways. So therefore, if you, in a simple ways, if you multiply these equations by this value, surely we know that this part of the portion will be gone. That means we have only 1 by f d square f by d phi square only. Therefore, if we have this, it is totally separate. So this phi, f is also a function of phi only. It does not contain r, it does not contain p. Therefore, this can be equated into any constants and insert here. Then you will find only r and theta here. Therefore, if you equate it to these equations, we get simply one equations. That means this equation. We know that this type of differential equation will give as solutions, what type of solutions, and in quantum chemistry, what type of solution is acceptable. As we know that this a sine theta or a cos theta or something like exponential of I x, all these 2-3 type of solution of this equation is acceptable. So we'll come later on this one. And the remaining, instead of this part, now we can write m square minus m square as we are given here and simplify it again. And finally, we separate the polar coordinate of quantum Schrodinger equations for hydrogens or hydrogen-like atoms into 3 parts. That means this is one equation, and this is one equation which contains only r, and this is Another equation which contains only theta. Therefore, that the coordinate equations for polar coordinates has been divided into three parts. That means the first one is only phi, and second one is only r, and theta, and another, the third one is only theta. And this is called, sometimes we call it radial equations, or we call, because it depends on the radius, and we call it r equations, or this is called theta equation, and this is called phi equations. So therefore, if you move on, we know that the equation number 7 will have three acceptable solutions. However, if it is the motions is here about the hydrogen atoms, therefore the acceptable solution is only simply this one, where m has the value of 0, plus minus 1, or plus minus 2, etc. So therefore, this is the acceptable solution. From the first equation, we have a solution of this function, and the others theta equations. That means the theta equation can be solved, which we have explained in the other classes. So theta equations can be explained by taking the value of m. That means if you go back here, here this value of m consider as equal to 0, and if you consider value of m does not equal to 0, we got Legendre or associate Legendre equations. And if you have the associate Legendre equations, the solution of that equations will be Legendre polynomials. So the third equation solution is this one. Either in the short form we write like this, or in details we write like this, where x is equal to cos theta. So as this part of the equation has been solved separately in case of the rotational motion, so I may not go in detail here. And the next one is the R equations. Now to solve these R equations, you can see here these equations can be simplified by taking the assumptions of the Boy theory. That means where it is given as E is like this and A naught is like this, and therefore putting R is equal to rho and A naught by 2J. If you insert in these equations for this one, or for this one, or for this one, we get these equations. And if it is here, it is common, so we can take commons, and finally we got the simplified equations. So now from these equations, this equation number 12, to solve these equations, it depends to the value of rho. This depends to the value of this rho. Therefore, if the value of rho is very, very high, that means this high value will be divided to the small value, and this high value will be divided to the small value. That means these two value will be very small comparing to this 1/4. At the same time, this value will be very small comparing to this. Therefore, the equation becomes simply this part, and this part only. That means this type of solutions will have as solutions as simple as exponential minus rho by 2. And if the value of rho is very small, the solutions of that equations you can see in the above equations by taking the small value of rho, then you will get the solution as rho to the power L. And finally, that means we know for the high value of rho and small value of rho, that means if you say the intermediate solution of rho, what will be the solutions? We do not know. Therefore, but we can assume that L, which is the function, surely which will be the function of rho. Therefore, putting of this value and substituting in the above equations, that means in these equations, the value of rho, or the value of dr by d rho, and the value of d square r by d rho, we can simply found an equations. That equation is called Legendre equations, and that equations will give a solutions which is called Legendre polynomials. So that Legendre polynomial is given as the solution as given here, where p and k can be written as 2l plus 1 and k is equal to n plus l. Therefore, now we we divided the Schrodinger equations into three parts, and if it is three part, we'll have three solutions, and we'll have a three part of a normalized constant, because for each wave function we need to normalize it. So from the first equation we have one wave function, and from the second equation we have one equation. If you write them together, the hydrogen light atoms will have a wave function as like this. That means R part, which is depend to N and L, and P part, which is depend to L and M part, phi part, which is depend to the value of M. Therefore, if you write a complete wave function of a hydrogen atom, it will be psi NLM. So this is the total. If you put it together, all the three above three, this is the first solution equation, and this is the second part, and this is the third part. That means this radial part. Therefore, together this will give you the wave function. So therefore, if this is the wave function of a hydrogen atoms, and if this NLM is having a value, that means we consider them as principal quantum numbers N, and azimuthal quantum numbers L, and magnetic quantum numbers M. Now that means if you know the azimuthal principal quantum numbers, azimuthal quantum numbers, and magnetic quantum numbers, for example, for 1s orbitals, we can say N is equal to 1, and we can say L is equal to 0, and we can say M is equal to 0. That means we know we can easily solve this equation. That means when psi is equal to 1, 0, 0, then if you put all the value of this N, L, and M, surely we'll get a final wave equations. That wave equations which can be represented to the s orbitals, that will come to the conformations. Therefore, if you put all the value from the orbitals, that means 1s orbitals, that means 1s, for 1s it is given here, and for 2s it is given here, and this is for 2p, surely this is for 2p1, and this is 3 part is there, but we do not know which one is 2px and 2py, and surely this must be 2pz. That is definitely is 2pz. So we have the wave functions according to the value of N, L, and M, which is principal quantum numbers, azimuthal quantum numbers, and magnetic quantum numbers. So at the same time, if we go for 3s, it is here, and 3p, it is here. This 3 and 3d, this one and this one, which is 5. Here it is plus minus 2, and here it is plus minus 1, and it contains imaginary numbers I. Therefore, this cannot be a real wave function. So, however, from the above equations, that means from the above wave function, above this wave function, if you put the value of N, L, and M, surely we have a wave functions corresponding to the 1s, 2s, 3s, or 3p or 3d. So in the next class, we will see from these wave functions how can we conclude the shape of the orbitals. Or therefore, in the next part, we will continue, and I think we can continue on this slide. Therefore, with this wave function, if you continue, we can separate them into two parts. One is a radial part. That means, as we know, radial part means the equations with this R part is called radial part. Therefore, we can plot the radial plot. We know that the value of N and L for 1s orbitals, we know that N is equal to 1 and L is equal to 0. That means for 1 and 0, the wave equation will be like this. And if it is like this, if you put the value of, we know that A naught in atomic unit, and this is in the x-axis, and this is in the y-axis. And we know if it is in atomic unit, A naught is 1, and Z is also 1. Therefore, it depends only to the R value. That means if R is 0 at this point, surely you will get the value as like this. That means if this is also 1, if this is also 1, you will get 2. Therefore, this value is the highest at 0 point. And if you keep increasing the value of R, it will keep on decreasing. And for 2s, that means n is equal to 2, and L is equal to 0, we also have this, and here now it grows the axis. That means here we have a nodal point. That means where it goes into zeros. Therefore, it goes to the negative, and finally it come again, but it does not never touch the axis again. And if it is 3, we have two nodals. One is here and another one is here. So like this, from the we can do the radial plot. This has been in the graduation levels also, but we do not solve the wave functions, radial wave functions, which is coming from the radial equations. So therefore, if you plot for another 2p or 3p, then we can get the radial plot as like this, and I'm not going to take too much time here. So therefore, that is the radial plot. And if you go for angular plot, now we can see the psi 100. That means, as I told you, this is same as 1s orbitals. So the wave function is this one. Now in these equations, as I'm also giving in the explanations here, as you know, it depends only to the value of r. That is, when you keep increase for one value of r in x and y, if the value of r is 1, then the whole this area, just like a ball, will be covered. So therefore, it depends only to the r. Therefore, in all the directions, it will be covered. That means it will be look like a ball. So therefore, the s orbital set is spherical. So therefore, no doubt that this, according to this wave functions, this represent the s orbital. If you shoot 2s also, it will remain the same. However, because of this 2 minus zr, that means when you keep increasing the value of r, at certain point, it may be greater than 2, or it may be same as 2. If it is same as 2, it will be 0. Therefore, for 2s, we have one circles, another circles. That means at this point, it is a nodal point. That means where in the radial plot, where it touches the y-axis. So therefore, 2p, that means for s orbitals, we easily knows that it is sphericals. But for 2p, if you see cos theta, that means 2pj, that means 210, we know that it's belong to the z axis, because in the transformation of Cartesian coordinate to the polar coordinates, z is equal to r cos theta. Therefore, we can say this is 2pz. But for 2px and 2py, it contain an imaginary value. That means if you see the wave function here, you can see here it contain I part. That's why it cannot be a real form. Therefore, this cannot be a real form of the shape of the cannot be determines the shape of the orbitals. Therefore, we can add this 1, 2, 1 plus 1 and 2, 1 plus 2. 1 is plus, and you got this one. So it contains sine theta and cos phi, which is exactly same as x-axis in the transformation of Cartesians to the polar coordinate. And this one, if you subtract them, and we get sine theta, sine phi, which is equal to the y-axis. Therefore, we know that this belongs to the y-axis and this belongs to the x-axis. Therefore, this is called 2px and this is called 2py and this is called 2pz. So therefore, to determine the shape of this 2p p orbitals, we can see this, which is dependent to the theta and which is dependent to the phi and also which depend to the r. But in case of z, it does not depend to the phi, it depends to the theta and it depends to the r only. So therefore, if you see the shape of the p orbitals, we can see from here, when 2pz is independent of phi, if you change the angle of theta, that means angle theta from 0, 30, 60, you can see here, cos theta will have value 1 to -1. That means it goes at 0 at 90. That means along the z-axis, it comes to the 0, and finally it goes to the negative, and it goes to the -1. This is -1 maximum, and this is +1 maximum. And if you increase up to after 130, 180, it will keep going like this again. It will come here. So therefore, it is totally circulars in one part of other side of Z, and others on the positive side of Z. However, we know that the shape of the orbital is, as we know, that it is not circles. That will come later on. So therefore, p orbitals, this 2p will have one part in the negative side of the Z, and another part will be in the positive side of the Z. And similarly for 2px, it will along the x will have one part, one circular part, and another circular part on the positive and the negative side. Similarly, I'm giving here the angles, and you can see by holding a calculators, you can see is it this value is correct or wrong, and you can also plot from that wave function which is given above. And so similar, though we can say the simply from this, sorry, so from this wave functions, we can have some ideas of the structures of these p orbitals, or px orbital, py orbital, and pz orbitals. And about the as similar ways as in case of 2p orbitals, we use the trigonometry and we make into real form of d orbitals. And you can see dz square is a function of cos 2 theta, dz square which is given here. So therefore, if you put the value of theta in the different, you will find here theta will be 0, and it will vanish, and when theta is equal to 150, it will vanish at this. It will maximum as theta is equal to 0. That means it gives like this, and finally it increase again. Therefore, we come to know that the structures will have one part in the top of the z directions and another from the below, and in the middle there is one loft in this case. So similarly for dxy, dyz, dx square minus y square, dy square, I have given here the points where the angles become 0 and where the angles become maximums. So you can put the value of this theta and phi. That means here you fix phi and you change the theta, and that means another you change the theta or you change the phi. That means, as you know, the angle theta is the angle made on the z axis, and phi is on the plane of the xy made with the x-axis, and this is x and this is z. So you can try yourself that how it is the shape could be. So therefore, however, we know that the shape of the orbital is not exactly circulars. Therefore, we know that it is exactly ovals or dumbbells. So therefore, if you consider the probability, it is here. If you say the probability, we know that the probability means when psi square, if you consider the psi square, that means whatever psi we have for 1s, if you square them, you will get this type of equations in atomic unit. And if you plot them, now the same wave functions in the square form, that means in the probability form, will give you a little bit ovals, and finally we can say that this is exact the shape of the orbitals. So if you plot the wave functions in a probability, angular probability, then in psi square, where we know that this psi square is the probability of finding the particles. So we get exactly the shape of the orbitals for p or s or for d orbitals. So this is about the hydrogen atoms and hydrogen light atoms in the quantum chemistry. And from here we have the ideas of the shape of the orbitals of s orbitals, p orbitals, and z orbitals. And thank you.